Hello everyone. Very good morning. I'm Shantanu and I'm a member of the Punavasu Astronomy Club from Dolphin PG Institute of Biomedical and Natural Sciences. And today with me, I have Dr. Anupam Bhardwaj from the Korea Institute of Astronomy and Space Science with us, and Dr. Ashish Raturi, who's the head of Department of Physics at Dolphin PG Institute. So today is the beginning of the World Space Week, and this event has been organized to celebrate space. So I'd like to welcome our panel members, Dr. Anupam Bhardwaj from Korea Astronomy and Space Science Institute, Dr. Ashish Raturi, Head of Department of Physics, and all the guests watching this live and later. Today marks the first day of the World Space Week. World Space Week is an international celebration of science and technology and their contribution to the betterment of the human conditions. The United Nations General Assembly declared in 1999 that World Space Week will be held each year from October 4th to 10th. These dates commemorate two events: October 4th, 1957, as the launch of the first human made Earth satellite, Sputnik 1, thus opening the way for space exploration, and October 10, 1967, the signing of the Treaty of Principles governing the activities of states in the exploration and peaceful uses of outer space, including the moon and other celestial bodies. World Space Week consists of space education and outreach events held by space agencies, aerospace companies, schools, planetaria, museums, and astronomy clubs around the world in a common time frame. It aims to provide unique leverage in space outreach and education, educate people around the world about the benefits that they receive from space, encourage greater use of space for sustainable economic development, demonstrate public support for space programs, excite young people about science, technology, engineering, and math, foster international cooperation in space outreach and education. In 2020, more than 6,500 events were organized in over 60 countries under the theme Satellites Improve Life. The theme for this year, World Space Week, is Women in Space. While our topic is not under the direct theme for this year, I want to express our collective admiration to all the women in the fields of STEM who, despite the unfair hardships, inequality, and social expectations, rose up in their respective career ladders and inspired a generation of children following them. I'd like to share how this topic for the live lecture came to be. In the beginning of August, I was reading some papers on astronomy when I came across the work of Dr. Anupam in collaboration with Dr. H.P. Singh from the Delhi University. The two have published papers studying the properties of variable stars in various galaxies and clusters, and my favorite instance was the use of these stars to actually create a 3D morphological map of the host galaxies. Variable stars are definitely something very curious, and I feel the need to learn more about them through experts themselves. Today, the 4th of October, was a perfect opportunity to discuss something out of this world. Punavasu, the Astronomy Club of Department of Physics, Dolphin PG Institute of Biomedical and Natural Sciences, has been created with the vision to popularize astronomy and make it more accessible to students and public from all areas equally. We are thankful to everyone currently joining and supporting this cause by being a part of this event. I'd just like to remind all participants that there will be a Q&A in the end. So you can post your questions in the comments and we will relay as many of them through our guest speaker, Dr. Anupam sir. Without further ado, I'd like to invite Dr. Ashish Raturi to welcome our guests. Please, sir.
Thank you, Shantanu. And in the beginning of this event, I would like to quote a famous educationist and our first president of this country, Dr. Sarvapalli Radhakrishna. Uh, he quotes that the chief purpose of our education is not acquiring only the bookish knowledge, but the chief purpose of our education should be that we have to think about the space and more than the space in time. So, with this quote, good morning to everyone. It's really delightful to have all of you here today, and it's my privilege to welcome you all and our chief guest, Dr. Anupam Bhardwaj. We at Dolphin PG Institute of Biomedical and Natural Sciences, Dehradun, are providing quality education to the young students and to develop them as a professional in the biomedical and natural sciences since 2002. The institute is affiliated with HND Gurwal Central University, Srinagar, Gurwal, and recognized by UGC under Section 2F. We offer the courses mainly in the stream of paramedical, life, and natural sciences. We also offer programs in the commerce and the education stream. And as far as the physical science is concerned with this institute, we have started our journey in year of 2015, and there is no looking back since then. Over the last 5 years, the department is growing with time, with its developing state-of-the-art laboratories for learning through the experiment. We have a strong postgraduate program in physics. The curriculum of MSc Physics program is based on UGC choice-based credit system and provides in the depth study of the subject and related areas. The foundation of the subject is built through the core courses coupled with the choice-based exploration of different branches of physics through elective courses. Our department maintains active research for the uh, carrying out collaborative and interdisciplinary research. Our department offers science-based outreach programs for various schools in the state. Besides this, the department offers large number of science-based activities for providing wide spectrum of options to the students to pursue their interests. Department is also recognized as a NPTEL local chapter from IIT Madras. Dear participants, as you know, the Department of Physics of Dolphin Institute always brings to you the intellectuals from across the globe for enriching our students' knowledge base in several ways. And in this continuation, today we have a cosmos personality from the intellectual domain of this country. He is none other than Dr. Anupam Bhardwaj from Korea Astronomy Space Science Institute, Republic of Korea. I welcome you, sir, and thank you very much for accepting our invitation to deliver your talk on variable stars as a cosmic distance ruler. And I hope it will be very insightful talks for our students, and definitely you will able to push them from their comfort position to the new horizon of this cosmos universe. Thank you, sir, and I welcome you again. Thank you.
Thank you so much, Ashish sir. And now, before I hand over the stage to Dr. Anupam, I'd like to introduce him to our fellow viewers. Dr. Anupam Bhardwaj is a Boya postdoctoral research fellow at the Kavli Institute for Astronomy and Astrophysics, Peking University, and has been awarded the Gruber Foundation Fellowship for 2020. The Gruber Foundation has created the fellowship with the aim of promoting the science of cosmology and other branches of astronomy. The IAU Executive Committee recognizes this contribution to science and shares the desire of TGF to give this distinction to the highest possible scientific standing and international character. Besides this, Sir has also been awarded various other fellowships and honors highlighting his excellent academic journey, like the ESO Studentship in 2016, Research Fund for International Young Scientists by National Natural Science Foundation of China, KIAA Fellowship, and Boya Fellowship by Peking University, all in the year 2018. Dr. Bhardwaj received his PhD in astronomy from University of Delhi, India in 2018. He then joined KIAA as a Boyer postdoctoral fellow in May 2018 and was awarded as an outstanding postdoc in 2019. He is currently investigating pulsating stars as a mean to develop a better understanding of stellar evolution and cosmic expansion. Dr. Bhardwaj is also researching on stellar evolution and promoting the measuring exactitude of extragalactic distance scales as an independent fellowship in East Asian Core Observatories Association since 2020. On behalf of the institution and the club, it is my honor to welcome Dr. Anupam Bhardwaj and invite him to share his wisdom and knowledge with us today. Please, sir.
Okay, thank you, Dr. Raturi and Shantanu, for this introduction and for the invitation to talk about my science here. And good morning to all of you. And I hope that at the beginning of this Space Week, I can take you to a journey of stars and the universe, and try to give you an insight on how astronomers measure distances to the celestial objects that we see. So the topic of this talk is variable stars as cosmic distance rulers. So I will try to explain all the terms that I'm going to use in this title. What are the variable stars, what are the stars in general, and what are the astronomical distances. And in particular, the ruler term here has two meanings, which I have intentionally put in because, first of all, rulers in a sense that stars will be used to measure astronomical distances, but also in a sense that variable stars are excellent in doing so. So in particular, some of these stars like Cepheid variables have ruled this field for more than a century now, and they can be called, undisputed king of astronomical distance tracers in our galaxy and beyond. So these are in principle rulers of this field of astronomy. So to begin with stars, what is a star? We know it's a big ball of gas, not just a big ball, it's a gigantic ball of gas. And these are formed in stellar nursery, what we call star forming nebulae. So these are basically big clouds of dust and gas, mostly hydrogen and helium. So what happens is that deep inside these nebulae or the clouds, some of the parts or chunks gain enough masses and become more dense so that they can collapse under its own gravity, and they form protostars. So these protostars then can keep on growing by accreting gas and dust around from the environment, and then become pre-main sequence stars before reaching the main sequence. So not all of this material that they accrete goes into the formation of stars. So some of the dust remains dust as it is, or it is used to form planets or asteroids, comets, etc. So once the star reaches the main sequence phase where it spends most of the lifetime, then it depends on its mass how the star is evolved. So if we look at the structure of the star, it depends on a number of things, whether the star is at hydrostatic equilibrium, thermal equilibrium, what kind of opacity is there inside the star, what kind of energy transport, what mode of energy transport is taking place. So there are a number of factors involved. But if you talk about Sun, which is the nearest star and the most well-studied star, we know very well how the internal structure of Sun looks like. So what we have is a fusion core, right, where the nuclear reactions are taking place. Then you have radiative zone and a convection zone where the energy is transported accordingly. Then you have the photosphere where photons are emitted. So what we see comes from the stellar photosphere. Then we have chromosphere, which is nothing but just the atmosphere of the stars. In case of Sun, you also have corona, where you have stellar winds and flares and things like that. In terms of stellar evolution, as we know that the lifetime of stars is much larger than the human lifetime, so it's impossible for us to actually look at a particular star and see how it is evolving. So how do astronomers do it? They look at the stars at different phases of stellar evolution, right? So you can so in a traditional way, this is to put it together. It is done in a Hertzsprung-Russell diagram, so which is nothing but a luminosity versus temperature diagram. So in this diagram here, you can see that there's a main sequence where the stars spend most of their lifetime, right? Then there are, if you go towards the upper right corner, there are massive stars. On the bottom left and in the bottom right, you have the smaller objects. If you look at the colors, so blue is the hotter stars and the red are the cooler stars. What is important here to point out is this Cepheid instability strip, right, where the stars are not stable. They are prone to pulsations, which makes these stars variable stars. So I will come to this point later, but it is important here to notice that there is a certain region in the HR diagram where you can find the stars that are pulsating. So life cycle of a star. So once we once these protostars are formed from these star-forming nebulae and they start growing by gaining masses, then it depends on what is the initial mass of these stars at the main sequence phase. So depending on the initial masses, they will further evolve. For example, the low mass star, the sun-like stars, they reach the red giant phase, and then at the end stage of the red giant phase, they become planetary nebulae, which is just the unstable. They become unstable, and all the gases is shed away in a beautiful explosion, and then at the end stage of that, or the core of that, remains as a white dwarf. If the star is massive enough, it becomes a red giant, and the end stage of that is the supernova explosion, where the core collapses and you get an end product is either a neutron star or a black hole. So this is the general description that we know of. Of course, there are more ingredients or more things that happen at different stages, but that's for more detailed discussion. So what is the topic of interest today is variable stars, right? So what are variable stars? In the simplistic way, you can say all the stars are variable, right? Because during their life cycle, they evolve from one stage to other to their end stage of their life cycle. So they vary in their luminosities, obviously. But what we call variable is where we can detect magnitude fluctuations over the time scale that we are able to observe them, right? So maybe a few seconds to a few years, or maybe a few tens of years. So if you look at this plot, it shows a variability tree. It's a general variability classification, and it's not necessarily complete, but this includes both stellar-like sources and also non-stellar-like sources. So from the top, you can see that the variability tree is divided into two parts. One is extrinsic and the other is intrinsic. So intrinsic means that when the star is varying its brightness due to something intrinsic to the star, something happening inside the star. Extrinsic is when there is a certain extrinsic phenomena that is causing the variations in the apparent brightness of the stars. So in the extrinsic ones, there are of course stars, most importantly the binary stars, where during their orbit, one of the star eclipses the other, and depending on the line of sight, you see the variation in the luminosity that you observe from the binary pair. There could also be extrinsic variation due to rotation. So stars, some of the stars have uneven surface brightness on their surface, maybe due to spots like sunspots. So depending on which part of the star you are seeing along the line of sight, you can see the variable brightness variation if you observe it for a longer duration. Of course, there are also microlensing events. What is microlensing is basically you have a background source which is emitting light, but there's a foreground object which is massive, and then due to the gravity of this, the light gets bent and you see variation in luminosity, or you see enhanced luminosities or things like that. Of course, the extrinsic variability is also observed in non-stellar objects like asteroids, where the light from the sun gets reflected, and then because the asteroids are not necessarily symmetric, so depending on what is the orientation, you get a variable luminosities. Right? But what we are interested in is in the intrinsic and in stars, and in particular the pulsation in stars. So we'll come to the point where we find out why these pulsations are important. But as you can see, even within the pulsation branch, there are numerous kind of variables. Right? What we will focus on a very small group of variables that are pulsating radially. Right. So the pulsating stars, so as I said, I will focus on radial pulsation. So what I mean by radial pulsation is that your star is basically expanding and contracting radially, right? So the expansion or the variation in the size is spherically symmetric. In case of non-radial pulsations, some parts of the star move inward, the other move outward. So the phenomena that happens there is due to the pressure and gravity modes. Right? So, but our interest today is only radial pulsations. So among radial pulsations, I'm highlighting 4 different types of variable stars. One are classical or type 1 Cepheids. These are most important tracers of distances for not only in our own galaxy, but also for the extragalactic objects. Then there are type 2 Cepheids. Then there are RR Lyrae and also Mira variables. So if you look at the plot on the right hand side, you see classical Cepheids within the instability strip represented by this delta Cepheid, which is the prototype of these stars. And you can see there they span a long range of luminosities. These are quite bright. And these are also intermediate mass stars, typically 2 to 10 solar mass. So they undergo, so this is the 0 is main sequence. And if you look at these small numbers, if you can see 5, 10, 20. So typically Cepheid is around 2 to 10 solar mass. And since these are massive enough, once they cross the instability strip, if the Cepheid is massive enough, it also undergoes a couple of returns back and makes a couple of loops within the instability strip, which we call blue loops. Type 2 Cepheids are fainter, so these are divided in different subtypes depending on their evolutionary states. So BL Hercules are called post-horizontal branch. They represent post-horizontal branch evolution. So this is the 0 is horizontal branch, and post-horizontal branch is somewhere here for BL Hercules stars. Similarly, for W Virginis stars, they are trying to evolve post-horizontal branch moving towards the AGB, but they also make temporary excursions to within the instability strip. RV Tauri stars are also post-AGB stars. Right? RR Lyrae are low mass stars, and they are located at the cross section of the instability strip with the 0 is horizontal branch here. Miras, on the other hand, I've included these here because they are also very useful for distance indicators, but they are not located within the instability strip, right? So pulsations in Miras are slightly different. These are AGB stars, asymptotic giant branch stars, and I will come to the point why where pulsations in Miras occur. So why do stars pulsate? So if we talk about stars within the instability strip, what happens is that you consider some sort of perturbation that is causing, for example, the compression or expansion in the object. So if the star is contracting, the temperature is increased, and so does the opacity. If the star is hot, the pressure is higher. But as it gets compact enough, the radiation pressure starts dominating the gravity, and the star starts expanding, right? So it starts, as this star starts expanding, the opacity decreases, and then energy is released out. So this graphics will not play here because it's a PDF. So it keeps moving. So the star will increase the brightness as after this stage. But once it has expanded enough, there will be decrease in temperature and the opacity, and the pressure will be lower, so the gravity will dominate, and the star will starts to contract, right? And then you see the variation in the luminosity accordingly. Here you can see that the size of star is shown to be quite different, but which is not true, because the variations in the size for Cepheid and RR Lyrae stars are only 5 to 10% during their pulsation cycles, so it is not very significant, but the size in luminosities is quite significant because the temperature variations dominate. So when we talk about pulsations, these can happen at different in different pulsation modes. So just if you remember 1 and organ pipe, how the oscillations happen in those. So these can the pulsation can occur in fundamental mode, first overtone mode, second overtone mode, depending on how many nodes are there inside the star. So the pulsation in stars within the instability strip is attributed to kappa mechanism. So these are predominantly work for radial mode pulsations. So how are pulsating stars used as distance indicators, right? So if you want to derive a simple equation from this comes from the period mean density equation for a gaseous sphere. You can derive this equation, and if we know Stephen Boltzmann law, this is just a logarithmic form of that law. So if you basically combine these equations and put R, replace R in terms of period, radius in terms of period, because you can write density mass over volume equals as R to the power 3. So if you replace their R in terms of period and mass, so there is obviously a mass dependence on period, but you can see there's a luminosity, this is a period, and this T effective is the temperature, which is equivalent to color. So it becomes a period luminosity color relation. So for Cepheids, a period luminosity relation was discovered by Henrietta Swan Limit, and since, as Santanu pointed out, this is this week is attributed to honor women in science. So she is one of the most people who worked as computers in Harvard College Observatory, and she discovered this period luminosity relation for Cepheids, which has worked wonders for distance measurements and have led to numerous discoveries in astronomy. So if you look at the plot on the right hand side, it's classical Cepheids in the Magellanic Clouds. So the large Magellanic Cloud and small Magellanic Clouds are the two nearby satellite galaxies. So if you look at here, you can see that there are two relations or two sort of linear progressions. One is the maximum brightness and the other attributed to minimum brightness for the same star. And the region in between is basically the color term, because we are looking at a two-dimensional plane, the period versus luminosity, not the color term. So whatever is the scatter in between is attributed to color. So in a two-dimensional plane, you can look at period luminosity color relation as a period luminosity relation, right? So you can basically standardize the luminosity of a star. So that's how these stars become standard candles in astronomy. Right? So before going further into that, well, let's talk a little bit about astronomical distances and why they are important. So if you look at in the simplistic way, if you look at the night sky, we see some of the stars are bright, some of the stars are faint, but that we cannot be sure which of the star is intrinsically more bright, because what we see is the apparent brightness. So we can find that the nearby star is obviously the more bright one, and the star which is further is a fainter one. But intrinsically, it is possible that the farthest star is faint simply because it is far, right? So if we know the distance to that star, it is possible that it is intrinsically more bright than the star that we are that is nearby. So the distance measurement is important, first of all, to study the intrinsic properties of the star, but not just for the star, but all the astronomical objects in the universe. So you can make the same argument for the galaxies, which are quite distant. So if you want to know the intrinsic properties of the galaxies, you need to know the distance, right? So since the astronomical distances are quite large, much larger than the usual SI units that we use, we need astronomical units to measure distances. So one astronomical unit is typically 150 million kilometers. This is also nearly equivalent to the distance from Earth to the Sun. There's also the higher, for the larger distances, we use light years. So light years is more than 63,000 astronomical units, and then there's parsec, which is 3.26 light year, right? So if you are a Star Wars fan, you probably remember parsec term used in the movie when there's a quote that Millennium Falcon made a Kessel run in 12 parsec. So there parsec is used as a unit of time, which is not true, because parsec is actually a unit of distance. So how does astronomical distance ladder work? So distance ladder is how do you measure distances to further and further objects. So for the nearby objects in the solar system, we simply can do radar ranging. You can just send a microwave to an object and which gets reflected and comes back to us, and then you can measure the distance to the objects in the solar system. But this is very limited to only nearby systems, right? If you want to measure nearby stars, then parallax method is the most precise one, because so what happens in the parallax method is that you measure the same object from two different orbits, or maybe the Earth is moving per year around the sun, so you look at the position of this star every year or every 6 months, and then you look at how much is the variation or how much is this parallactic angle that is made, and the inverse of this parallactic angle gives you the distance. So parallax distance to nearby star is the most accurate method to measure distances, because this involves purely a geometric interpretation. There's no physics or chemistry of a stars involved. But if you want, but this is limited to very nearby distances, because if you go to the farther distances, then this parallactic angle becomes very small, right? And it's very difficult to measure. For larger distances, let's say within the Milky Way, up to 10 to the power 5 light years, we can use other independent methods such as mean sequence fitting to the clusters. So you have a cluster, you fit a model to the cluster, and then you find out what kind of distance, and the other variations in the luminosities that can occur due to extinction, etc. Give you the best fit of model with the observations. But here again, there are systematics in the models, and then this method is not that accurate. For the nearby galaxies, when you look at the extragalactic systems, the Cepheids are the most robust tracers for distance measurements because of their period luminosity relations, but there are other also tracers like Miras and RR Lyrae. They can also be used for distance measurements thanks to the period luminosity relationships. If you go beyond further in galaxy clusters, then the secondary distance indicators like type 1a supernovae, these stars dominate because those are much brighter. But further in the universe, if you want to probe the cosmological scales, then you look at the Hubble's law, where velocity dispersion versus distance, and then you can get distances depending on if you know the expansion rate of the universe. So typically the extragalactic distance ladder works with a cosmological goal to measure Hubble constant, right? And you can see there are scales on the left side, and there are different tracers or different distance indicators that can be used to reach the goal. On the right hand side, you can see there are Cepheids involved. Cepheids and type 1a supernovae have been involved, which is basically the most traditional way of measuring Hubble constant in the local universe. But there are also possibilities to use, you can see here, RR Lyrae, tip of the red giant branch. There are also planetary nebulae functions. These are all secondary distance indicators that can be calibrated with respect to Cepheids or RR Lyrae or other independent primary distance indicators. So as I said, one of the motivations that comes from the cosmology is to measure Hubble constant. So Hubble constant is a very important cosmological parameter because the inverse of it gives the age of the universe in simplistic way. So this is very crucial to constrain the age and the distance scale of the universe. If you measure Hubble constant at the local universe means our nearby universe when the redshift is 0. The Hubble constant parameterizes, or it gives you how fast is the universe expanding, right? So as we know from the standard cosmological model, dark energy is the most dominant constituent in the universe. There's also dark matter, and ordinary matter is very small. So we know we know about very small fraction of this of our universe. So why is Hubble constant measurements very crucial? Because these can be used to constrain the dark energy density in the universe and also understand the nature and the amount of dark energy. Right. So in the plot on the left hand side shows you very roughly how well you can actually constrain the equation of the state of the dark energy if we know very accurate or precise measurement of the Hubble constant. So 1% measurement of Hubble constant gives you a 2% constraint on the equation of the state of dark energy. So you get to know, so you can constrain basically if the dark energy is, for example, time dependent in nature or not, or things like that. Right? So if we look at the Cepheid based distance ladder, as I said, that this is the most traditional way of measuring the Hubble constant. So in this, Cepheids play the role of the primary calibrator. So if you look at the bottom left panel, so this is where only Cepheids are at play. So you can get individual parallax distances to Cepheids in the Milky Way. So you can then get their absolute luminosities, or you can look at Cepheids in the nearby galaxies like Large Magellanic Cloud, M31 and 4258, because for these galaxies we know other independent geometric distances very accurately. So then you can also calibrate their period luminosity relation. So when I say calibrate, that means you can convert their apparent magnitude into absolute magnitudes. So you get a very accurate calibration of period luminosity relation for Cepheids in the first step. Then in the second step, you look at the Cepheids in supernovae host galaxies, right? Because those Cepheids will give a distance to the supernovae, and the peak magnitude of type 1a supernovae is also a standard candle. So you can basically get peak magnitude of a type 1a supernovae because you know the Cepheid based distance to the host galaxies, right? So then in the third step, you go into supernovae into the Hubble flow and use supernovae magnitude redshift relation and this relation, and then you combine it to measure H0 in the Hubble flow. So this figure comes from the supernovae and H0 for the equation of state of dark energy SHOES project, which is being led by Adam Rees, who was one of the Nobel laureates of 2011 in physics for the discovery of accelerated expansion of the universe. So this is a very hot topic at the moment that is going on to measure Hubble constant using different stellar standard candles. So coming back to pulsating stars, as I pointed out, these are key standard candles. So how to measure distances using period luminosity relationship? So in a simplest way, we define distance modulus as the difference between apparent magnitude and absolute magnitude of an object. Right? So you can write distance modulus also in terms of the distance. So this distance d is in parsec. So 5 log 10 of d minus of 5. So here apparent magnitude comes from observing the star, right? Absolute magnitude is something that we need to quantify or standardize so that you can use those to get the distance, right? So apparent magnitude, as I said, is an observable quantity. And if you look at the variation, like I showed you, the periodic variation in the light curves of these stars, then you can easily get the periods if you observe the Cepheid or other distance indicators for a long enough time scale. And then for a given period, which is an observable, you can get the absolute luminosity or brightness, right? Because you have already standardized your period luminosity relation. So once you know both M and capital M, you can easily get a distance. So in a more practical term, how does it happens? So you have to, if you want to get, for example, a distance to a galaxy, So what you have to do is, first you have to observe that galaxy for a long time, at least. So for example, if you are doing if you are using Cepheids as distance indicators, then the minimum period of a Cepheid is 1 day. So you have to observe it at least for 1 full day, so that for the minimum period Cepheid you get you can estimate period very accurately, right? Then you do the photometry and you get light curves. Light curves is basically the variation in luminosity as a function of time. So then you know, if you see the periodic variation, you can tell that okay, this looks like a Cepheid variable, and then you can determine the period depending on looking at the light curves, right? And from the period, and you already know the apparent brightness of these stars, you get a period apparent magnitude relation. Now you need a calibrator relation. Calibrator relation means the same period luminosity relation, but now in absolute luminosities, right? And this comes from either in our own galaxy, as I pointed out. If you know the geometric parallaxes to individual Cepheids in our own galaxy, then you can get a period absolute magnitude relation. Or you can go to the nearby galaxies where the distances to the galaxies are very accurately known. For example, the Large Magellanic Cloud, right? So we know, so if we look at the Large Magellanic Cloud, we will see a relationship like this, but we know the distance to the LMC, so we can get this convert this apparent luminosity to the absolute luminosity, right? So you get a calibrator relation, and then you simply subtract the 0 points of the calibrator and the your target galaxy, and you get a distance modulus from which you can get a distance, right? So of course this works under the assumption of universality, that the relation does not change from one galaxy to another galaxy, that is, Cepheids are universal rulers. And what is very important to note here is that precise calibration is a must, right? Because if your calibration is not accurate, then your distance in the external galaxy will not be accurate. So coming back to pulsating stars, because these provide the absolute calibration, so you can use either of these tracers or your distance indicators to obtain extragalactic distances. So again, I've already defined classical Cepheids. These are intermediate mass stars. These are also young stars. So one important point here is to note that these stars, the ages of these stars. So these young stars, Cepheids, are typically 10 to 300 mega year old. Type 2 Cepheids are low mass stars. These are old stars. RR Lyrae are very old stars. These are 10 giga-year old stars. Miras represent intermediate to old age stellar populations. So why is this age important? Because there will be, so if you are looking at some young star forming galaxies, you will find classical Cepheids in there, right? But you will also find old stars in there, because there would be a previous epoch of star formation. So the stars that formed at earlier times will now be old. But on the other hand, if you are looking at the galaxies where only old stellar populations are dominant, so there are no ongoing star formation, so you won't find classical Cepheids there, right? So then you have to use some other distance indicators like RR Lyrae or Miras to obtain distances. So this is also important when you are looking at the type 1a supernovae host galaxies, like which kind of tracers you can use to estimate distances to those galaxies. So if we look at the color magnitude diagram or Hertzsprung-Russell diagrams, but in observational studies we call it color magnitude diagram, and it looks much more complicated than the earlier one that I showed, but you can still see that there are differences in the luminosities and colors for the different kind of tracers. So Cepheids are quite bright. Type 2 Cepheids, depending on different subtypes, they form these three different clusters. These are RV Tauri's, W Virginis, BL Hercules here, and RR Lyrae are the most fainter of these three or these four type of distance indicators. Myras will be somewhere here. These are AGB stars, right? So these are the AGB sequence. So if we look at the numbers here, so you can see classical Cepheids. These are population 1, so young stellar population. RR Lyrae and type 2 are POP2 stars. As I mentioned before, the pulsations can occur in different modes. So the stars can pulsate fundamental mode, first overtone modes, or higher modes of even the mixed mode pulsations are also common. These are the mass ranges, the period ranges. Classical Cepheids typically 1 to 100 days, but the first overtone modes are cover a much smaller range in period. In case of RR Lyrae, these have a maximum period of 0.8 or 9 or say 1 day. Right? Overtone modes have much smaller period. Type 2 Cepheids, they are divided into different subclasses based on evolutionary status and also based on their pulsation periods. And here you can see, depending on a sort of a comparison of what would be the luminosities for a given period of star, what would be the luminosities. So you will find that bright Cepheids are, the long period Cepheids are most bright ones, right? You can see the more the negative quantity, the more bright the star is. How do the light curves of these stars look and how do you classify those? So when you observe these variables, you get a light curve, right? But because there are similarities in the light curves for different type of variable stars, you need to classify them quantitatively, right? So if you look at the plot on top here, again, there are not much differences between fundamental mode Cepheid and fundamental mode RR Lyrae, except if you can see here, there's a slight bump that occurs in the RR Lyrae light curves. Similarly, if you look at the overtone light curves for Cepheid and overtone light curves for RR Lyrae, they look quite symmetric and more sinusoidal, right? So the differences are small, but the differences in the period are quite significant because these are longer period ones, Cepheids. RR Lyrae are shorter period ones. So one way of these one traditional way of classifying these stars is to look at the Fourier analysis, because these stars are periodic, so you can fit a Fourier series to them, and then look at the Fourier coefficients. And the certain combination of Fourier coefficients are constructed where which basically separate the light curve parameters of different kind of objects on different planes, right? So here these are amplitude and phase parameters. You can see there's an overlap of certain classes, but also you can see, for example, RR Lyrae and Cepheids are quite distinct on these plots, and you can easily classify them together with the period luminosity relationships. So if we look at classical Cepheids, so classical Cepheids, as I've said, they have been used extensively for distance measurements, and they have a very long history of distance measurements. So they were discovered. The first Cepheid was discovered by Ed Peggott in 1785, and then Goodricke observed variability of delta Cepheid, which is now known as the prototype of classical Cepheid variables. Cepheids in the Magellanic Clouds were discovered in 1908 by Henrietta Swan Leavitt, and she later on went on to discover the Cepheid period luminosity relations 4 years later. So with the discovery of Cepheid and Cepheid period luminosity relations, it became Edwin Hubble discovered Cepheids in the Andromeda galaxy. At that time, in fact, it was known that only Milky Way is the only galaxy, and Andromeda galaxy was considered as a nebula, a gaseous nebula, just another star-forming region of our galaxy. But when Edwin Hubble discovered Cepheids in the Andromeda galaxy, he found out that the distance from the Cepheid period luminosity relations for these stars is much, much farther than what is known for the galactic stars, right? So that time, then he knew that, okay, this has to be another galaxy outside of Milky Way. Then he went on to measure distances to several galaxies in the Virgo cluster, which is another cluster of galaxies, and also measured the velocities for recession velocities for those galaxies, and he found out a famous Hubble law, which tells you that the farther is the galaxy, the faster it moves away from us. So that gives you the first evidence that the universe is actually expanding, right? So the slope of this velocity dispersion law gives you the Hubble constant, and he estimated the earliest in his earliest estimates, Hubble constant values were quite far. He found something like 500 kilometer per megaparsec per second. So which implied, so if you take the inverse of the Hubble constant, it implied that the universe is just somewhere 2 giga-year old, right? Which is too young, because at that time, the dating of materials, something like carbon dating and all these things gave evidence that the Earth is much older. So it's not possible that the universe is younger than the Earth itself, right? So in fact, that those measurements were revised. So if you see in 20s, right, the Hubble constant measurements are quite large, but come 2000, these reduced by more than nearly an order of magnitude reduction in these measurements. So in fact, this discrepancy was resolved somewhere around 1950s by the discovery of type 2 Cepheids, because what Edwin Hubble used was a mixture of type 1 and both classical and type 2 Cepheids, which follow different period luminosity relations. So once that discrepancy was resolved, all the Cepheid-based measurements were more realistic, of H0 were more realistic. But there was actually, in 1970s, there's a famous Hubble war between two different groups, which were finding H0 measurements either in the 50s or in the hundreds. So there's at least 2 times uncertainty on the age of the universe, right? And this went on for quite a long time, right? So there were these research articles at that time which says, one of these says that there are just 2 unavoidable experiences, death and taxes, but cosmologists will add another one, which is the argument on the Hubble constant. In fact, this has not stopped. So this Hubble war was resolved when the Hubble Space Telescope was launched in 1990s. So in 2001, HST Key project on extragalactic distance scale, this found a value somewhere around 72, 73, and resolved this discrepancy very accurately. Since then, however, we also have independent cosmological measurements from the early universe by missions such as WMAP and Planck. So Planck measures the cosmic microwave background fluctuations, and with a standard cosmological model, it gives you a Hubble constant value in the early universe. But with H0, with Cepheids, you can measure Hubble constant in the late universe. So at the moment, there is a tension between early universe measurements, which are on the top, and the early universe measurements on the bottom here, and the late universe measurements in the top here. So this discrepancy is currently being termed as Hubble tension, and this is quite significant because if this discrepancy holds, that means there is something missing in this standard cosmological model. So there has to be some new physics that needs to be accounted for this discrepancy, right? So this is one of the hot topics that are ongoing in the variable star community at the moment. So coming back to Cepheids as distance tracers. So as I said, you need, first of all, to measure accurate distances, you need a very accurate calibrator. So classical Cepheids in the LMC play a crucial role as calibrator of the period luminosity relation, right? So in the pre-Gaia, so if you know, you probably heard of Gaia mission, which is an astrometric mission. That means it measures the position of stars, and if you keep doing that for many periods, then you can get very accurate parallaxes, right? So you get very accurate distances to number of stars, to in fact a billion stars in the galaxy, right? So in the pre-Gaia era, there were only few stars with parallax measurements, right? So it was very difficult to derive a period luminosity relation in absolute magnitudes for Cepheids in our own galaxy. And in fact, this problem is true for all other kinds of variable stars, whether you are talking about Cepheids or RLI or Miras. But in the Gaia era, which is still ongoing, there are the order of the increase in the sample size is quite significant for Cepheids with accurate and precise parallaxes, and similarly for other type of variables. So in fact, with new Gaia parallaxes that were released earlier this year, you can calibrate Cepheid period luminosity relation with a 1% precision. So you can get a distance to any external galaxies with 1% if you do good enough measurements in that galaxies. These are the pre-Gaia measurement that I did a few years back. So you can see in the absolute magnitude versus log P relation, it itself was pretty good, but now the improvements from Gaia have reduced the scatter and also the systematics that are involved. But there are still quite a few things that one needs to take care of when using Cepheids as distance indicators. The first thing is this works under the assumption of universality of these relations. So how universal these relations are, this is what you have to justify. Whether these relations are linear over the entire period range, that is another point to note. What are the metallicity effects? Because you are looking at the Cepheids in different stellar environments, in different types of galaxies. So what are the effects of the composition? What are the effects of the extinction? So extinction is how the dust affects the luminosities of these stars in certain galaxies, in the galaxies they live. So before Gaia, the nearby Large Magellanic Cloud has served as an independent anchor of the distance ladder. So if you look at the plot here, these are again the period luminosity relations in different filters. This is for fundamental mode and first overtone mode. So if you look at the GHK relation, these look much tighter than the galactic relations ones, because LMC is farther at 50 kiloparsec from us. So any variation due to variation in distance of Cepheids within the LMC will not make much of a difference, because for us they are all at same distance in the Large Magellanic Cloud. So looking at the near infrared, why I pointed out that you should look at the near infrared, because in the near infrared wavelengths, the period luminosity relations are much tighter, and you can see this in the plot as well. Why does it happen? Because in near infrared, the temperature fluctuations are smaller, right? So within the instability strip, so the instability strip is narrower. So whatever the temperature variations that occur in the optical wavelengths, it gets reduced at infrared wavelengths. There is also a smaller sensitivity to extinction, and also the metallicity effects, and also the amplitudes of these. Variability amplitudes of these stars are smaller at longer wavelengths. So you get accurate mean magnitudes from a small number of infrared measurements. Right. So another point is for the universal, as I pointed out, you need to test the universality. So what you can do, how you can do that is that you look at the Cepheid period luminosity relations in different galaxies. So this is in our own galaxy, this is in the LMC, and this is in the SMC, and then you compare if there are any variations in the slope, or if there are any variations due to metallicities and things like that, and then you can quantify. If there are any differences, you can quantify those as a systematic uncertainties and say, okay, we can do this accurate measurement of distance using Cepheid variables. There are also issues of extinctions, as I pointed out. So for extinction, as I said, if you go to the longer wavelengths, the effects are smaller. So it's better if you do it at say 3.6, 4.5 micron wavelengths, but you can also do it in near infrared GHKS wavelengths, or you can also construct some reddening independent functions such as called Wesson height magnitudes. So Wesson height magnitudes is nothing but a period luminosity color relation where color term is taken into account such that these effects become minimal. So you get a Wesson height relation. So if you just look at this term here, this is WVI, and if you go back in and look at V and I period luminosity relation, they exhibit much larger scatter as compared to WVI, which is a Wesson height magnitude, because it has taken into account the color term. There are also theoretical approaches to look at the period luminosity relation. So for theoretical approaches, you need to do modeling. You have to do the stellar pulsation modeling and then construct a Cepheid model given the composition. So you can use composition, for example, representative of Cepheids in the LMC or in our own galaxy, and then you then try to generate Cepheid pulsation models and generate light and velocity curves, light curves at multiple wavelengths, and then from the light curves you can look at the period luminosity relation. So this is one such period luminosity relation that comes from purely theory. So here you can see there are different sort of sequences, and also the scatter is large at optical, but it gets reduced again in the infrared. So these different sequences represent a range of physical parameter that go in as input to the pulsation models, because models cover a much wider range of physical parameters like masses, luminosities, temperatures than what you would actually see in a particular galaxy, right? So you see a much larger scatter in these relations. But how do you know if these models are actually representative of Cepheid variables or not? So for that, you can just compare with the observables. So you know the period and light curves from the observations, and then you can generate the same thing from the theoretical models as well, and then do the comparison, quantitative comparison in some way, for example, simply using Fourier analysis or some other sophisticated methods, right? So this is just one quick example to show how you do it. So this is one of the light curve parameters that I've explained before. And the black points here are the data points, right? And the colored points are models with parameters, right? So this shows variation as a function of mass for models. This shows luminosity, this shows temperature. And you can see that there is quite a bit of consistency with the observations, except for some of these models, right? Which fall in a region where there are no observations. So you can exclude that for this galaxy these models are not appropriate, or if the parameters that are input for these models, those are not suitable for Cepheids in a particular stellar environment, right? So this is how you can get best models to derive theoretical calibrations of period luminosity relations, and also to better understand the physics of these stars in terms of what is the impact of masses, luminosities, temperatures on the evolution of Cepheids, and give better constraints for stellar evolution and pulsation models. So this is again the same plot, now showing how the variation in the slopes occur as a function of wavelength, right? So on the top panel, it shows the variation of slope as a function of wavelength for the galaxy, LMC, and the theory. So you can see that at the shorter wavelengths, the slopes seem to be consistent, but if you go at much larger wavelength, theoretical slopes are slightly offset. But if you look at the Wesson height relations, which I previously told you are independent of reddening, then there is a consistency, and also the variations, regardless of which wavelength you use, are much smaller. So it goes from 3.0 to 3.6, but here you can see the variation is much larger. So that's why Wesson height functions are now preferred to estimate distances than the simple period luminosity relations. Okay, so I'm not sure how much time do I have, but I will go through RR Lyrae variables. So let's look at now RR Lyrae variables. These were discovered as globular cluster variables, right? So these are found primarily in the clusters when they were discovered. But the prototype RR Lyrae was a field star, so this was not associated with a cluster and it was discovered in 1901. So again, for RR Lyrae as a distance indicators, first of all, these are population 2 stars, right? So they are found in galaxies of all types, unlike Cepheids, which are found in only in star-forming galaxies, right? They also follow a very tight period luminosity relation in infrared, but these are much fainter than Cepheids, so these are difficult to find at much larger distances, right? Also, the calibration of RR Lyrae period luminosity relations in the galaxy is still issue, but again, this is being resolved with parallaxes from the Gaia. And these stars are being proposed to obtain Hubble constant as well, to complementing another POP2 distance indicators, which are tip of the red giant branch star, which are not variable stars, so those I have not included here. But since these are both population 2 stars, they are found in all types of galaxies, so they can be used to measure H naught, similar to providing an alternative to classical Cepheid supernovae distance ladder. So as I said, these variables are found in globular clusters, so they also led to quite a few discoveries. So if you look at the period amplitude diagram for these stars and then look at the mean period and mean metallicity of these stars, so Ostroff discovered that these clusters are distributed in two distinct types. So one is Ostroff type 2 and Ostroff type 1 cluster, which have different properties. So type 1 is more metal rich with a smaller mean fundamental period of RR Lyrae, and the O2 ones are more metal poor clusters. They have larger mean period, right? And this way then you can try to understand how these globular clusters, the stellar populations in different globular clusters evolve in different stellar environments. So if you look at the period amplitude diagram as well, then you can see that the different O1 and O2 clusters have different sequences, and these sequences can be reproduced with models of varying parameters. So Y here is the helium content. So you can see that helium content plays a crucial role in defining what is the minimum period of RR Lyrae in a given cluster. So this way you can constrain the composition of the stars. You can try to better understand how the evolution happens from systems of different mean metallicities and a number of things. But focusing, going back to RR Lyrae as distance indicators, so they follow a visual magnitude metallicity relation, which was traditionally used for distance measurements. But there are a number of systematics involved in that relation. So period luminosity relations at infrared wavelengths is the obvious choice, right? So the plot here shows the period luminosity relations in 3 different clusters. So you can see this is very tight relations again, right? But one of the issues for RR Lyrae distance measurements is that the metallicity dependence is quite significant, right? It's much more significant than that is observed for Cepheids, right, where it's quite small. So if it is quite significant, then you have to add another term in the period luminosity relation and make it a period luminosity metallicity relation, so that you can get very accurate distances even using RR Lyrae stars. So for that, this is one of the projects that I'm involved in. So I just quickly show. So you can do that by looking at RR Lyrae in globular clusters of different mean metallicities. So you can see this is again the Hertzsprung-Russell diagram shown as a color magnitude diagram. So you can see this is the main sequence, and then you see this is the AGB part. This is the horizontal branch where RR Lyrae are dominating in all these clusters. You can see there are in one of the clusters there are also Cepheids. These are type 2 Cepheids, not classical Cepheids. Classical Cepheids will be much brighter. But you can see that there are a number of RR Lyrays of different types, fundamental mode, overtone mode. There are also RR Lyrays which show amplitude and phase modulations, which is called Blasco effect. So the idea is that you look at the period luminosity relation. You look at the period luminosity relation for RR Lyrays in different globular clusters of different mean metallicities, and then you can derive a period luminosity metallicity relation. So you get a very accurate period luminosity metallicity relation. So you can see on the top panel there is a clear dependence on metallicity for RR Lyrays, which is not that significant for Cepheids. So you can measure distances quite accurately. But in case of RR Lyrays, you have to add a metallicity term to use these as accurate distance indicators. So again, you can do theoretical approach as well. So on the left, it's the observational approach. So you get empirical or observational period luminosity relations. On the right, you get period luminosity relation from the theoretical models, but for a fixed composition, so the metallicity spread is not there, which is seen in the cluster, which is seen in different stellar environments. So you get a very accurate. You can reproduce the observational period luminosity relation, and then use even the theoretical period luminosity metallicity relations to estimate distances for RR Lyrays in external galaxies. Just quickly on Miras as well. So Miras are quite bright. Again, these are AGB stars. These are quite bright stars. So if you look at in infrared, so Miras are long period, right? They have periods of 100 to 1000 days. So if you look at 230-day Miras, at longer wavelength, it has a magnitude which is similar to Cepheid with a 50-day period, right? So these are as bright as Cepheid. But the problem with Miras is that these are long periods, so you have to observe the galaxy for a much longer time than the Cepheids. Also, these stars exhibit they have extended atmospheres where there is a lot of dust, so they undergo what is called the circumstellar extinction. So this is not just the normal interstellar extinction that I was talking about earlier, but there is an additional source of extinction. Since these are AGB stars, they undergo mass loss, right? So that is another point. These are present in older populations similar to RR Lyrays, but unlike classical Cepheids, so they can be used where in galaxies where classical Cepheids are not present. So if you look at the phase here, you can see that at maximum light, these are brighter and smaller in radius as they become fainter, at the phases where their sizes are large. So you can look at Mira period luminosity relations at mean light or even the epoch of maximum light to get very accurate period luminosity relations. So you can see Mira light curves are like this. You can see you have to observe them for a long time. So these are decade-long light curves to get very accurate constraint on the periods of these Miras, because the periods of Miras are often quasi-periodic. So these are not strictly periodic like Cepheid and RR Lyrae stars. But you get a very good period luminosity relation for these stars even at maximum, whether you use the mean light properties or the properties at any other maximum light pulsation phase. So you can see the Miras have different chemistry as well, just like Cepheids and RR Lyraes have fundamental and first mode classifications. This also happens for Miras, but Miras are also divided in oxygen-rich and carbon-rich Miras, depending on the amount of surface, depending on their surface chemistry. And you can see that they have very nice period luminosity relations even at optical wavelengths, so not necessarily at infrared wavelengths. So I have looked at Myras in more recent times to complement my efforts for Cepheid and RRI stars, and you can see that if you look at the two nearby galaxies, the LMC and SMC, you can get a very accurate distance using Myras to these galaxies, and also estimate very accurate relative distances, both using optical and infrared properties. Right. So these properties will be quite useful for Myras, especially when you see that there are upcoming large telescopes and also these large time domain surveys, such as the LSST of Vera C. Rubin Observatory, which will run for 10 years. So you will get a number of long period variables in different extragalactic systems. Just for the last stellar tracers, type 2 Cepheids. So type 2 Cepheids are not that popular as classical Cepheids and other distance indicators. This was because they have different subclasses, and different subclasses represent different evolutionary states. So in terms of evolution and physics and chemistry of these, they are not very well studied. But you can look at these period luminosity relation. You can see that these are still quite tight, quite well, so that if you can find them in abundance in some systems, then you can use those to determine period luminosity relations and estimate distances. So this is for the Large Magellanic Cloud. Again, you can see from I to G and GHK, there is quite a bit of scatter. So that's why these are not as dominantly used as other distance indicators. So with this, I think I will stop and just show you some of the take-home messages. So what I would like to point out that you should remember that these pulsating stars are basically one of the most robust tools to estimate extragalactic distances, not just extragalactic, but also in our own galaxy. This is all because of their proper pulsation properties, which give you a period luminosity relation, which becomes tighter at infrared wavelengths due to several properties, such as the limited temperature variations within the instability strip. Cepheid variables have been long used as primary calibrator of the cosmic distance ladder to measure h0, the expansion rate of the universe, and they continue to play an important role in doing so. So in general, Cepheids are very sensitive probe for the stellar evolutionary and pulsation studies, but also for cosmic expansion. There's one important point that I have not discussed is to explore the morphology and structure of extragalactic for the extragalactic systems. So you can use, because once you get very accurate distances, you can use three-dimensional maps of the galaxies in which Cepheid and RRI rays and Myras are available. But one important point to note is that there are large time domain surveys that are ongoing, and also there are large telescopes that are coming. So stellar variability, which is time consuming because you have to monitor stars for a longer time. But now with these surveys, you will get these automatically. So these studies will get even more revolutionized in the near future. So it's an ideal time to work on variable stars at the moment. I'll stop here. Thanks.
Thank you so much, sir. This was a very interesting talk. I hope everyone who's viewing it right now share the same feeling. Thank you, sir. Sir, so now we'll be taking up some questions that we have on our comment section. I'll just read this. Sir, so we have a question from Gaurav Yadav, and he wants to ask that why do Cepheids show blue loop nature in the instability strip?
Why is blue loop?
He's asking that why do Cepheid stars show blue loop nature in the instability strip?
Yes, so Cepheids are at the central helium burning evolutionary phase. So both Cepheid and RR Lyrae are at those evolutionary phases. So what happens is that when the star, when you look at the Cepheids of low masses, so say 2 to 3 solar masses, they make from the main sequence they go towards right, and then they reach when they cross the Cepheid instability strip, right? They so for the low mass Cepheid you don't get blue loops because the first evolution through the instability strip is quite fast, right? It's very rapid, so you don't get you do not catch Cepheid in that phase. But for the higher masses, in the central helium burning phases, they undergo multiple crossings through the instability strip. The reasons are mainly because of the central helium burning phase. It depends when they go towards the right, the temperatures, the temperature variations occur, right? Both in the outer cell of this outer helium burning, hydrogen burning cell, and inside the inner helium burning cell of the Cepheids, that changes their luminosities and the temperatures. So it goes towards the cooler temperatures, but then becomes slightly brighter, but then it comes back towards the blue colors, that is hotter temperatures, and then this keeps happening up to 3 times only. Right, so even for the most massive ones, it can have only 3 crossings through the instability strip. There are also rotation effects that make it happen, right? But that's another point. So there are also the convective overshooting. So there are quite a few phenomena that are interlinked in producing the variation motion within the instability strip for these stars.
Thank you, sir. So he also asks that can pulsating stars change color? Am I audible, sir?
Sorry, there was a break up in your voice.
Right, sir. So he also wants to ask that do pulsating stars change color?
Okay,
I'll show it in the screen, sir, once. Do pulsating stars change color? That's his question.
Yes. So pulsating stars change color during their pulsation. So if you look at the light curves, you can see that it goes from the minimum brightness to the maximum brightness, right? And then if you look, when you are trying to find a color, you need to observe it in 2 filters, right? So in the filter one, it goes like this. In the other filter, the variation may not be similar to the shorter wavelength. So let's say you are looking at the optical band V band and then in infrared band J band. So the shape of the light curve is different in the V and I, right? So when you subtract the variation as a function of pulsation phase, you will see that the colors vary depending on what is the variation in different bands as a function of pulsation phase. And this is also evident within the instability strip because the temperature is varying, so the color is also varying.
Right, sir. So our next question is from Prashant Prasad. And he's asking that is the absolute magnitude greater than the apparent magnitude?
Okay. I again lost you when you started asking question.
So he's asking that is the apparent magnitude greater than the absolute magnitude?
What is the absolute magnitude?
So he's asking that is the apparent magnitude greater than the absolute magnitude?
So magnitude is what you see, right? So it's a different quantity, what you see, right? Absolute magnitude is what is intrinsic to the star. So absolute magnitude is defined what is the magnitude of any star at a distance of 10 parsec, right? So you measure, so apparent magnitude is greater than absolute magnitude. It's numerically, it's possible because numerically it's true because absolute magnitudes are negative quantity. In astronomy, the brightness goes as, as a negative value. So more negative the number, the bright the star is. So small m is, you usually have positive numbers because what you are doing is you are observing stars as apparent brightness. But if you account for the distance, which is large, then you get the absolute magnitudes, which are quite bright. So numerically, they will be small.
Yeah,
Right, sir. Thank you, sir. Yes, sir. Ashish,
one
sir, you
question.
have a question.
Okay.
Yes, sir.
Thank you, Dr. Bharadwaj. Really, it's a wonderful insight you gave to our students, and really, it's a
Lost.
very
Ashish, sir, I think you're not audible, sir. Uh,
Am I audible?
uh,
Yeah, now, but sometimes when the
Okay, maybe
question
some network problem is
comes,
here.
you know,
Santanu, is it okay?
there is a break on
um,
your side.
there's a little break at times.
Okay, I think it's okay
Ashish, sir,
now.
I can. Yes, sir.
1 minute. Is it okay? I think
Yes,
Yeah, for
Ashish, sir.
now.
okay. Dr. Bharadwaj, I would like to ask one question on behalf of the students and on behalf of my own. That as being a faculty of in the university, we have a lot of constraints to over the exercise over the practical aspects of the astrophysics. I think you well aware about this because as far as astrophysics is concerned, we have a need of more various sophisticated instrumentation or spectroscopy as well. So, can you suggest some open source data repository regarding the astrophysics data by which our students can access them so they can practically. Uh, am I
Sorry,
audible?
yeah, the voice keeps breaking up on your side. So
Okay.
I heard like practical application of astrophysics, something like that. The question is related.
Yes, yes, yes.
Sir, I think
Yes, yes,
Ashish sir wants to ask that are there open source data archives?
Yeah, switch off my video. What happens?
Okay, so I guess we've had a small network disconnection from Anupam sir's side. So we'll just take a minute break. I request all the viewers to just stay connected for a minute.
Yeah, sorry about that.
Not a problem, sir. Sir, shall I repeat the question? Is my voice clear now? Is my voice audible, sir?
Yeah, I can't. Yeah, hear you. It's breaking. Your words are breaking all the time. Am
Okay,
I
so
audible
tell me
here?
one. Yes, sir, you are. We can do one thing, sir. I guess you have a private chat option available, right, sir?
Okay.
Uh, so I'll just type the question over there and you can read it out and answer, sir. Would that be comfortable?
Yeah, sure.
Perfect, sir. Sir, so I'll just type Ashish sir's question. So I've sent the message, sir.
Yes, so there are plenty of sources or resources for the analysis of variable stars. So in fact, what is happening now? Yeah, so what is happening now is that with these large telescopes, whatever the data comes, it is available on science archives. So there are multiple choices right? Whether whether you want to do uh, research on data that is already reduced, already processed. So you just look at, you extract the data, data in a sense that for the variability studies, you need light curves, right? You need observational measurements in different filters for a range of time. So if you have that, then you can do many studies. You can do classification analysis. You can try to develop machine learning methods on how to classify different types of variable stars. You can do stellar structure studies. You can do galactic structure studies. So there are a number of sources, number of catalogs. For example, Google catalog of variable stars, which has provided basically the largest catalog of pulsating stars in the galaxy, in the galactic bulge, in the Large Magellanic Cloud, in the Small Magellanic Cloud so far. Then with Gaia as well, with Gaia mission also keeps publishing these successive data releases. So with DR2, they have produced uh, these light curve catalog for variable stars. So there are a number of resources that one can look at. Also, there are some GUI softwares like VStar that gives you all the basic analysis, period determination, and things like that for variable stars.
Thank you, sir. Sir, our next question is by Samantha Smith, and her question is that what are the factors that determine the luminosity period relationships?
Yeah, so this, as I said, is comes from the pulsation equation or period mean density equations. So it's not just for the pulsating stars, but even for a gaseous sphere, right? So if you are looking at a gaseous sphere and then look for its expansion and contraction, and then see how the velocity of sound moves in the interior of this gaseous sphere, then from that you can derive an equation called pulsation equation, right? So from pulsation equation, and when you look at this simple Stephan-Boltzmann law, right, which is and you combine these, you get a period luminosity color relation. So the main factor there in the period luminosity relation is the color term, because you're neglecting that. It's a three-dimensional picture and you are looking at the two-dimensional picture. What factors would contribute to this? So there are contributions of obviously for a number of parameters, because in the period there is a dependence of mass, right? So there's a period mass radius relationship that comes from stellar evolutionary calculations for Cepheids and also for RLI rays. In terms of luminosities, that depends on the composition, right? What is the composition of star? What is the metallic content? What is the helium dependence? So intrinsically, mass, luminosity, temperature, composition will play a crucial role in determining what would be the luminosities and periods of these stars.
Thank you, sir. I hope that answers the question of our viewer. Sir, our next question is from Mr. Rajesh, who wants to know, how do we determine the metallicity of a star from the spectrum?
Yeah, so if you have a spectrum, then you can look at the spectral lines. So there are iron lines, there are silicon lines, there are calcium triplet lines, and then you look at the equivalent width of these lines, what is the width, and then you have a series of stellar spectral libraries for different parameters. So typically, what is the temperature, what is the log G, what is the metallicities, and then you fit the theoretical or stellar spectral libraries with the spectra that you obtain, and you find the best fitting spectra that gives you the stellar metallicities and temperatures and all those things that you can determine. Yeah. It's not as straightforward. In fact, the spectroscopy is probably much more complicated than the photometry, where you just image the star, and then you look at the number of counts that you get and convert those counts into the in the magnitude scale, and you get the apparent magnitude. So yeah, but there
So,
are tutorials to learn how to do that.
thank you, sir. So, talking about photometry, the next question is from Mr. Dibakar, and he wants to know that can he get light curve data from CDS portal?
Yeah, yes, you can get from the CDS. So there are, but it depends. So there are certain papers or publications that publish the light curve data that they analyze, right? Like even for several of my publications, you can find the data that I have. So there are data that are extracted from the Science Archive that is usually not published. You just put the link of the Science Archive. But if you have done observations yourself from a certain telescope, then you have reduced that data and then you have extracted the light curves, then you can, then it's ideal that you publish that for the community so that if one wants to reproduce your work or use your data for some other analysis. So it's available on CDS, VGR, number of, or the just the journal link. You go to the journal paper and then there are supplementary materials and you can find the light curve data there.
Thank you, sir. Sir, so the last question, I guess, would be coming from me then. And sir, I want to ask you that what are the future prospects on research on this topic using open source data? What's
Well,
the
the prospects are enormous because the amount of data that is going to come up in the next 4 or 5 years is monumental because observatory will be online, so they have the legacy survey called LSST, which will go on for 10 years. Series data for several hundred galaxies for millions of variable stars. So you'll not only be limited to smaller telescopes that are doing very nearby galaxies time domain. Then there are also large surveys, large telescopes that are coming up, and they also have a time domain component in their science. So you can probe much farther, right? So you can probe to the distances that have not been explored so far with 30-meter class telescopes. So you will come to know, you will get able stars at a distance of 20, 30, 40 megaparsec with an unprecedented precision that has never been done with even with what HST has done at these distances, that will be improved significantly with JWST. So yeah, the prospects are a lot.
Thank you so much, sir. That is something I really wanted to know that where the future research from this point can go ahead. So before we bid farewell to our viewers, I just want to request you to say a few words. Okay, Ashish, sir, you want to say something?
Yes, yes. First of all, my apology for the disturbance. I think it's due to poor
Audible,
network here.
sorry.
But Dr. Anupam, really, it's a wonderful talk given by you. And in near future, I would like to request to you, whenever you get back in India or your hometown, please share with your schedule, and definitely we will welcome you here offline at our campus. And we would like to hear more from you. Thank
Okay,
you.
thanks. I guess that was an invitation to visit
Yes,
visit
yes.
you because the words keep breaking up. So yeah, thanks. I will look forward to it. Yeah, sure. If I be in
Thank you.
Dehradun or somewhere around, I will definitely give a message.
Sir, so now I hope all the questions have been answered. And with this, I would like to thank Dr. Anupam Bhardwaj for his educational session. I really enjoyed learning about all of these interesting variable stars. And I hope the feelings shared by the viewers are mutual. And we'll be updating everyone with any future events, and we'll be sending out the certificates for this very soon. So thank you, everyone, and have a nice day.
Thank you.
Thank you, sir.
Ciao.
Anupam, sir, I'll just request you to stay for 5 minutes once we end this.
Okay.